Module, I plan to cover two topics. The first one is the heap sort. Second one is the hashing technology. Okay, two topics. Yeah, this module. I plan to use 2 weeks. Yeah, to complete this module. Yeah, this week and the next week. Then after that, our last week before the final, right? So our regular classes, we have 3 weeks before the final week. Yeah. So I will use 2 weeks complete module 5. The last week, third week, I will use for review for the final. So 2 classes, I will do 2 review sessions for the final exam. Okay? Yeah. All right, first, let me talk about the arrangement for the final exam. Yeah, so one student asked me that question. So I feel I should talk to the whole class to give you, our final round arrangement, assignment arrangement, and including the final exam. All right. Our final exam still part A, part B. I split 2 parts. Yeah. Because in that way, I can put a part A online, right? Yeah. So you do not need to do the whole, 25 questions in that 2-hour period. Yeah. So split 2-hour period, you only do part B in that 2-hour period. Part A, you can work at home, okay, like a quiz, quiz type. Yeah. All right, so final exam. All right, so here I want to emphasize it's a 2-hour test. Yeah, Yeah. Then, yeah. Part A, part B. Yeah. Yeah. So similar to our homework assignment number 3. No, number 2. No, we don't have number 3. Number 2. Yeah. Yeah. All right. So part A. Ten questions. Concept questions, all right, yeah. Then that will be, I will use that as our quiz number 6, yeah, because quiz number 5, we need to practice. We need to practice module 5, we need to do quiz number 5. Yeah, yeah. Then after that, our last quiz number 6, the same as the part A of final exam. Yeah. I still give you about 1 week to complete quiz 6, the final part A. Yeah. So I can give you as early as possible, okay? The earliest possible time of that final week. Yeah. Well, that final week, the whole week. But I try to assign as early as possible, okay? At the beginning of that final week. Yeah. Then you have a whole week to complete. Yeah. Yeah. All right, so that's part A. Part B, 15 questions. Computation questions. Okay, yeah. And at this time, I will now split part B, part C. Remember our midterm 15 questions, I split part B, basic questions in classroom, part C, hard questions online, because this time it's different from midterm. Midterm, you only have 75 minutes, right? 75, if I give you 15 questions in 75 minutes, that's too hard to complete, right? So in that way, I split 10 plus 5, 10 basic questions you need to complete in 75 minutes. But this time we have 2 hours, right? So I don't want to split. 2 hours, let us do all the 15 questions in that 2-hour period. How about that? How about that? Including the hard questions, but hard question I will control, doable, not too hard, okay? Yeah, not too hard. So the hard questions I define. So here we use the similar format, 10, so that's 15 questions, all right? So here I talk about part B, 15 questions, 10 still basic questions. Five hard questions. But those hard questions I do not define, as very hard. Okay, just you need to. So here I say, you need to use some kind of tricks. Okay, you need to do something special. Yeah. It does not mean you need to do a lot of work. Yeah. Some little trick, here, there. Yeah. Non-trivial. So you need to do some, creative work. Yeah. A little bit creative work. Okay? Yeah. Find a solution. Yeah. So you need to solve some technical difficulties, yeah, that kind of thing. Not too easy. Okay, not too easy. Yeah, a little harder than the basic questions. So I control in that level. Yeah. Okay. Yeah. 5. Yeah. So then because I do not want to split. Yeah. If it's split online, drag you too long. So yeah. So I try to make it as simple as possible. So you complete it in that 2 hours. When you leave, so you forget about it. Yeah. 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 And 15 questions in 2 hours, it should not be that hard, right? At least doable, right? So not that, Yeah. The questions, all old questions. So I do not give you brand new questions. Okay? Yeah. I mean the style, the content questions you have seen before, yeah. But you need to work on some different conditions. Yeah. Work on some different conditions. Yeah. Things like that. Yeah. Yeah. Any questions you can ask?
Is it going to be similar material policy as the midterm? So
Yes. Open notes. You can use your computers, calculators. Yeah. But when you use computers, do not do that, online search, search engine, AI tools, do not use those things. When you use computers, yeah, let me tell you, when you use, what usages are legal for the final? One, calculator, legal. Online calculator, okay? Like Wolfram Alpha is legal. Okay, if you use Wolfram Alpha, that advanced calculator, that's legal. Yeah. All right. Access our course materials, that's legal. Okay. Yeah. Yeah. Illegal, search engine, illegal. AI tools, technical forums, those illegal. Okay. And communication software, illegal. Okay. Yeah. Yeah. All right. So that's the policies. Okay. Yeah. Yeah. All right. Other questions? Yeah. Oh, ready? No, not accumulative. That means we cut off after midterm. Okay? Yeah, the questions after midterm. So not that comprehensive, accumulated, not that. When you do preparation, focus on our current homework assignment. Homework assignment number 2. Okay? Yeah. And let's say, so use your homework assignment number 2 to tell you, what questions you can expect in the final. Yeah. Okay? Yeah. But definitely, so here, but one more thing. So although here I say homework assignment, but I need to, do some reasonable change, because homework assignment I already assigned, it does not cover module 5, right? So module 5 we have a few more questions, right? So module 5, although the quiz number 5 will cover concept questions, but module 5 we will have several computation questions. We will have a few computation questions. But the computation questions we will not have chance to practice, right? We will not have, because we will not have another assignment. We do not have the time to do another assignment. So we have no chance to practice computation questions from module 5. So what I'm going to do, remember in the review session, right? We have 2 review sessions. So the first review session, I will give you several sample questions from module 5. Sample questions, okay? Several computation sample questions from module 5. You just use my sample questions as examples. Then you work on the question in the final from module 5. Module 5. You have sample questions. So, but I need to change it a little bit. From sample questions. So that's the difference. If you compare homework number 2B questions and the final exam part B questions, that part is the difference. Part. The module 5 questions. Okay. Module 5 questions, 3 or 4 questions. Let me say 3 or 4 questions. I will not give you too many. Minimum 3, maximum 4. Okay. Questions from module 5. All right. Other questions? You can ask. All right. So then let me move to the 8.1, Introduction to Heapsort. All right. So here, another sorting algorithm. So let's count how many sorting algorithms we have learned so far. Okay. Selection sort, bubble sort, insertion sort, merge sort, quick sort, heap sort. This is number 6. This is number 6. and I do not want to say the last one because at the end of this module, I try to give you another interesting sort. Another interesting sort. It's quite different from all the current 6 sorts we have learned. It's different. It's a little special. So I want to cover that one at the end of this module. So we should have plenty of time for that. Counting sort, another counting sort. That's our number 7. So in this course, we will learn 7 different sorts. Okay, all right. The question why we need to learn this, another new sort. Sorting with special requirements. Here, I want to emphasize the special requirements. So it's not a general sorting we want to deal with. Not general, but sometimes So when you solve the real world questions, you need to sometimes some special requirements are added to your problem. Yeah. So you need to prepare that. When you need to meet those special requirements, then you need to do things differently. Yeah. So here, let's look at what are those special requirements. Yeah. All right. The first one, the worst case efficiency should be in this category, big theta of n log n. Look at this first requirement. First requirement, if you look at our, those 5 sorts we have learned at this point, only one satisfies this requirement, right? Only one of the 5. Merge sort. Merge sort, the worst case is in big theta of n log n. Other than merge sort, the other 4 not qualified. So the first requirement, we eliminate 4 of the 5 sorts. Yeah. Quick sort is not qualified. Quick sort, worst case, big theta of n squared. Too slow. Okay? Yeah. So the reason, you may ask why people, want to put this first requirement. The reason is they want to avoid the bottleneck. Yeah. Because that n squared, it's a bottleneck. Okay, very slow. Yeah. But for some of the special applications, so people want to avoid that kind of bottleneck. Yeah. So put this requirement. Okay. All right. So that's the first one. Second one, in place. All right. So this concept I need to explain here, because the meaning is different from our previous. We learned the in place meaning. It's different from this in place. We're talking about in place algorithms. The previous, when we talk about, we call it in place elements, right? Yeah, elements in place or not. Here we call the algorithm is in place or not. So the concept is different. So I need to explain this in place concept. Yeah. All right. So here I want to talk about in place algorithm. What algorithms are in place? Yeah. Regarding using the space resource, when you design an algorithm, other than the efficiency consideration, you also need to consider the space usage, right? The space resource usage. Second important. Yeah. Efficiency is the first important thing. So space management, second important. Yeah, but also important, but less than the efficiency factor. Yeah. So for that space usage, yeah, if you use too much memory space, then your algorithm can, still not good enough. Yeah. So we want to control the memory usage to some acceptable or, not too bad. We want to make that control. Yeah. So we want to remember in our quicksort, we talk about using auxiliary arrays, right? Auxiliary arrays. Yeah. So the auxiliary array you use pretty much the same amount of space as the original data storage. You store your original array, same amount of space. That kind of space usage, too much. Okay, too much. So here, we remember later, we eliminate the auxiliary arrays, right? After we eliminate array, the extra space we used, just a small number, right? Yeah, one extra space used for swap, another for storing the control the S region, index variable control the S region, another J extra space used to control L region, and so on. Finally, finite number of extra space used. Yeah. So here we define. Here we do not say finite number of extra space used. So here we say this way: extra space so what's the meaning extra space? Extra space means you use the space other than the storage space used for input and output. For input output, you have to use. For any question, you need to store input output, right? Yeah, so we treat as the normal space usage, not extra. Yeah. But other than the storage for input output, if you need extra storage space, for that part we call it extra space. That extra space used must be in this big O of 1. Big O of 1. You know the meaning, right? Yeah. Yeah. Bounded by constant. So the exact meaning, big O of 1, the number of extra space used, okay, bounded by a constant. Yeah, constant number. Okay, even 100, it's a constant, right? Yeah, but must be a constant. That means when you enlarge your data size, 1 million, 1 billion, that constant never changes. Okay, that constant, whatever it is, it never changes. So bounded by a constant. Yeah. If your algorithm has this property, then we say this algorithm is in place. Yeah. So it is an in-place algorithm. That concept. Yeah. Okay. Yeah. Also, it's an important concept. Yeah. All right. Then here, the requirement number 2, we require this sort must be an in-place algorithm. That's the second assignment, second requirement. Yeah. All right. Now let us use this concept to check our previous 5 sorts. 5. Okay. Before this one, we have 5. All right. Yeah. Yeah. Let me check one by one. Okay. All right. The first one, selection sort. In place or not. Now, the extra space used. Yeah. Think about that. Selection sort. Swap, right? Selection, we just, not swap. We store the maximum, right? Yeah. So then, swap that maximum, Yeah. Selection sort. Yeah. Yes, right? It's in place. Yeah. Extra space, small number of extra space used. Yeah. Then next one, bubble sort. Also in place. Yeah. Swap. Okay. Also in place. Yeah. Insertion sort. Insertion sort. Yeah. In place or not. In place. Okay. Shift operation, right? Yeah. Compare, shift. Limit, small number of extra space used. Yeah. In place. All right. The third one, merge sort. Merge sort. Not in place. Remember, when we do the merge, we need to copy the data to some destination array. Your destination array, you use the size. So that's not bounded by constant, right? Your destination, a lot of extra space used. So the merge sort, not in place. Yeah. Then quick sort. How about the quick sort? In place or not? Yeah. Quick sort, yeah, it's a little harder than the merge sort regarding this in place or not question. Yeah, why it is hard? Yeah, because for the quick sort, that partition step is in place, right? Partition step, because we eliminate auxiliary arrays, then the extra space we use very limited. Yeah, I just mentioned. But that's just the one partition step is in place. It does not mean the whole algorithm is in place, right? Yeah. So the quick sort, if you talk about the whole algorithm, it's not in place. Why? Let me explain why the whole algorithm is not in place. Yeah. Because the quick sort, we need to do recursion, right? Recursion, yeah? Recursive, divide and conquer. The conquer step, we need to do the recursive function call. So when you do recursion, how can you use constant number of extra space to do recursion? You cannot. Recursion, we don't use a lot of extra space, right? Yeah, because when we do the recursion, yeah, so here, I need to use some space to draw. You need to use a stack, right? Yeah. And many recursive function call you push into the stack. Yeah. And the stack could be very deep. Yeah. You know, the depth of the stack. You know, you cannot control. How to control, right? Yeah. Yeah. Very deep. The deep stack uses a lot of memory space. That's why we have the stack overflow problem. Okay, stack overflow problem. You can overflow the stack, you know, too big. Your memory cannot hold that big stack. So you have stack. Any recursive algorithm has this problem. Yeah, long big stack, that problem. So if you consider that factor, it's not in place. It is not in place. Yeah. So quicksort is not in place. Okay? Yeah. You need to consider the whole picture, not a part of it, right? Part of it is in place. It does not mean the whole algorithm is in place. Yeah. Yeah. All right, that's requirement number 2. This one must be in place. That means you cannot implement this algorithm using recursive function call. If you use it, not in place. You have to use a for loop to do it. Yeah, that's okay. For loop, we do not use stacking for loop, right? Yeah. For loop, we do not use stack. Yeah. So here you can see the difference. So in our implementation, we have to use for loop to replace the recursive function call here in this algorithm. Yeah. Yeah. All right. The third one, maintain dynamic data efficiently. Another important requirement. So what's the dynamic data? Yeah. When you apply your algorithm, so data comes in and go, you know, so you need to handle your data change, insertion. Yeah, you add a new data item, then later you delete. So you need to maintain the dynamic operations on your data. That means, because when a new data item comes in, you need to do insertion, right? Insert the added new data into the ordered array efficiently, right? Yeah. Because when you add a new data item, if it's not efficient, it takes a lot of time. It's not good. So when you add new data, you need to do that insertion operation efficiently. Here the question, what do you mean? What's the meaning efficiently? All right? Because when people say efficient or not, it may not be objective, right? Yeah. Different people, they have different understanding on this efficiency word, right? Yeah. So here, we should make it objective. Yeah. Okay? So what do we mean efficient? Yeah. Here. Binary search way, we treat efficient. Yeah. So the binary search way, if it's a big theta of log n, if you do insertion in this category, we say yes, efficient. Okay? Yeah. Linear search way, not efficient. Okay? So if you do the insertion in the linear search way, big theta of n, then not efficient. Yeah, yeah. People agree with this. Yeah. So that means when you insert a new element, you need to make sure it's in the of log n. Yeah. 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 All these three requirements, think about. Yeah. Yeah. None of our current sort satisfy these three requirements, right? Yeah. Merge sort. Yeah. Requirement number 2, yeah, eliminated. Okay. Quick sort. Number 2, eliminated. Right? Yeah. Insertion. Yeah. Dynamic. Merge sort. We don't know how to insert. Merge sort, right? Quick sort. Yeah. Yeah. We don't know how to insert. Yeah. No support. So for all the current sorts, they do not have built-in support for efficient insertions. How about that? No built-in support. Yeah. So this feature, when we need to add our new sort, we need to rely on some advanced data structure. That's the title of this module 5, advanced data structure. Yeah, because if you use array directly, yeah, our current data structure is an array. Yeah. If we use our array data structure directly, you cannot make it. Not advanced enough. Yeah. So here you can see, when we, yeah, because for this algorithm class, we emphasize the algorithm part. Actually, we know the data structure also important. Yeah. Yeah. So our main focus is at the algorithm side, but we need to know sooner or later, when you work on the problems harder and harder, then the data structure becomes more and more important. Yeah. So that's the reason in our last module, we need to touch that data structure topic. Yeah. All right, so here, we need to do some work in our data structure design. You need to design some special data structure, okay? Yeah. The main reason to use a different data structure, we want to organize our data, in an efficient way. Yeah. Organize our data to support our operations efficiently. That's the main reason why we need to spend so much time on the data structure. Yeah. All right. All right, yeah, so that's the, yeah, all right, so I talk about, yeah, all right. Then, new idea. So now we need to work on the data structure, yeah. Design. All right, how to make efficient insertion, yeah, and the log, yeah, so the log base 2 of n. Here you can see, if we organize our data in a binary tree structure, then we can do the log base 2 insertion. Yeah. Binary tree structure. Yeah. Array is not a binary structure, right? Array, the line structure. You can call it's a straight line, one line structure. But here we need a binary tree. Okay, yeah, multiple levels. Yeah, multiple levels. Okay, binary tree structure. Yeah, like this. Okay, and so on. Yeah. Then, when you organize your data in this way, the height. So here, the height concept. The height. Yeah, height is log base 2 of n. See, the worst case when you do insertion, the worst case is this log base 2 of n. So here, in order to get log base 2 of n insertion, you should organize your data in a binary tree structure. Okay? Yeah. All right. That's the design of data structure. All right. Now we need to review our data structure knowledge. Yeah. We have learned data structure, the course, right? Yeah. 2250. Let's review a little bit. Yeah. We need to select from our 2250 course which data structure we should select here. Okay? Yeah. Appropriate. Yeah. To store data in a binary tree. That's our goal. Store out the data in a binary tree. Yeah. Using the data structure. Yeah. Candidates. Yeah. Let's look at the candidates. Yeah. One is array still. Yeah. Although we know, at this point we don't know if array can do it or not. Yeah. But at least array we can put it as a candidate, right? Yeah. The second, yeah. Because when you need to store your data in a binary tree structure, binary tree, from this binary tree, you have root node, then you have nodes in different levels. And how do you specify the relationship between the nodes, among the nodes for different levels? Parent-child relationship. Because in order to store a binary tree structure data, you need to address the parent-child relationship. How to address the parent-child relationship? Okay, yeah, so here, another one method, linked list. There is link, right? Pointer, a link, point, you know, yeah. You can use links to, you know, point to left child, right child, right? Yeah. Left child node, right child node. Yeah. Parent node, right? Yeah. So, yeah. Linked list. So you put it in the candidate. Yeah. All right. But yeah, but here the thing is, linked list, if you compare it with array, it is a little more complicated, right? Yeah. Because people, so they feel, working on linked lists, you know, you need to do a lot of preparations, you know, working on pointers, yeah, or references, yeah, Java replace pointers by references. You know, avoid pointers. Okay, yeah, yeah. You need to spend a lot of effort on those links. Yeah, so that most people do not like that way. Most people do not like that way. Okay, yeah, working on linked lists. If you can avoid, then people like to avoid it, right? Yeah, make it as easy as possible. So the next question is it possible we can use array to do the job? Yeah. So our next technical problem we want to solve, we want to use array to do the job. So what kind of job? Addressing parent-child relationship. Then we can avoid linked lists. If we can address parent-child relationship in an array, then we don't need to use linked lists. Yeah. So the next question is it possible to find a way to address the parent-child relationship in the array? If it's possible, then we're happy, we just use array. Yeah. So that's our next question. We need to answer. Technical question to be answered. All right. Yeah. All right. So then, the question, yeah. Because if we use the array directly, then it's not good. If we use array directly, insertion operation is very expensive. Insertion operation will be in big theta of n. Yeah. So insertion. Here I'm talking about the direct way. Okay. The direct way not good is because the insertion op is in big theta of n. Big theta of n. Too slow. Yeah. All right. Yeah. So we want to add some structure information into this array. Yeah. We need to add something to an array. Otherwise, we cannot do insertion efficiently. Yeah. All right. Yeah. So there, the question, how to add the extra structure property in array, structure property in this array. Yeah. All right. So some smart idea. Here we need some smart idea. Yeah. The idea is not complicated. Yeah. It's pretty simple. The extra work you need to do, very simple, but the idea very smart. Yeah. Simple and very smart. So we need to build a binary tree structure in the array. So, yeah. All right. How to specify parent-child relationship. If you can find an easy way to represent parent-child relationship, then you solve the problem. That's simple. Yeah. Here, let me, look at the time. Yeah. I should not, spend too much time on something. Yeah. How to modify the array? Yeah. So data stored in the array. So, all right. Yeah. Here, you can assume it is sorted. Yeah. Because we want to maintain the array in order. Yeah. So even if the array is sorted, you can apply binary search, right? You can apply binary search. Yeah. All right. Yeah. All right. Yeah. Because when we maintain our data, every time when a new data inserted, so when we maintain the data, we can make the whole array ordered. If we want, make the whole array ordered. Yeah. All right. Yeah. So. Yeah, when a new data comes in, it's not ordered, but we want to make it in order, efficiently. So we need to do insertion, but the insertion we want to do binary search insertion, not linear search insertion. Yeah, the binary search insertion. Yeah. So the linear search insertion not acceptable. Okay, yeah. So our target is the binary search insertion. Yeah. So that's acceptable. Yeah. All right. Yeah. So the insertion, linear search, binary search, the difference is big. Yeah. All right. Next question. We need to make it. Yeah. So our direction, we want to do the binary search type insertion. Yeah. But how to make it? Yeah, so that's not easy. Yeah. All right. Yeah, so here we need to add new properties to our current array. Yeah. To make it more advanced. Like our current array is not advanced. Yeah. So make it a little more advanced. Yeah. All right. Yeah. All right. Yeah. So here, next we need to figure out how to represent parent-child relationship. All right, all right. Yeah. B.2, binary tree structure in array. Yeah. So let's look at the simple solution of the binary tree relationship representation. Yeah. All right. How to build a binary tree inside an array. Yeah. All right. So here we introduce this heap data structure. Yeah. Now, the special data structure heap comes in. Okay. Yeah. What is a heap? Yeah. 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 All right. People call it heap. Yeah. So in many other places, people use this heap word. Yeah. But in our algorithm, when we use this heap, we have our own special requirement we need. Yeah. Yeah. All right. So when you define a heap data structure, yeah, so we need to, follow these. Yeah. All right. What is a heap? Yeah. It's a near complete binary tree. Yeah. Yeah. A short description for the heap is near complete binary tree. Yeah. So you know the complete binary tree, right? Yeah. So you know complete binary tree. Yeah. Yeah. What is a complete binary tree? Yeah. 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 All right. For example, here I show you a simple complete binary tree. Yeah. One node here. Yeah. Next level, 2 nodes. Then you go another level, 4 nodes. This is a complete binary tree. Yeah. Complete. Yeah. Yeah. The nodes in all the levels are full. Yeah. All levels full. Okay. Yeah. You cannot add one more node in any level, right? Yeah. So all full. Okay. That's complete binary tree. Let me give you incomplete. Okay. Yeah. So for this case, incomplete. This binary tree is not a complete. Yeah. Yeah. Because in this level you can add more nodes, right? Yeah. 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 You can add more nodes. Yeah. In several levels. Yeah. Complete, you cannot add any node in any level. Yeah. All full. Okay. That's complete. Yeah. Yeah. But the possibility to have a complete binary tree relatively small. Yeah. Because only when your data size n equals power of 2 minus 1, then you can have this. N equals power of 2 minus 1. Yeah, 7 power of 2. 2 cubed minus 1. Yeah. 15. 2 to the 4th minus 1. Then you have complete binary tree. But in most of the cases, n is not equal to power of 2 minus 1. Then you do not have a complete binary tree. Yeah. So the next best thing is near complete, right? Yeah. So we add this word near. We do not require fully complete. Yeah, we do not require that. Yeah. All right. Yeah. So the question is, how do you define near complete? Yeah. So we just try to make it as close to complete as possible. Okay. Near complete. So what's that near complete? Yeah. So all the levels are full except the bottom level. We only, so if, yeah, because you cannot make all the levels full, right? But, so we allow the bottom level not full, okay? Not bottom level. Bottom level, we allow, you know, a lot of location you can insert new nodes. Now, other than bottom level, all other higher level, all full. Yeah, you cannot insert. Yeah. That's what we call a near complete binary tree. So a heap must be a, you know, look at the structure, must be near complete binary tree. Okay? Yeah. Yeah. That's the first step. Yeah. Yeah. Near complete. Yeah. Here. Yeah. All right. Yeah. All right. That sufficient space for dynamic data. Another question we need to consider. Yeah. Now we want to consider how to store the data. Yeah. So here, next question. Yeah. Store the data. Sufficient space. Yeah. Because think about when we need to use array. Yeah. So here, if you recall your 2250, you know, data structure. Yeah. So when you learn the pointers, yeah, management. Yeah. Think about the memory allocation. Yeah. So think about the memory allocation topic. When you need to store your data, first you need to allocate sufficient space to your array, right? Yeah, you need to do that. At memory allocation, okay? Yeah, yeah. When you declare an array, you need to specify array size, right? When you specify array size, then certain amount of memory space is allocated to that array. That amount of array allocated, okay? Memory allocation. Yeah. The question, but you need to store the dynamic data. What's the data size of dynamic data? How do you know the size of dynamic data? It keeps changing, right? If the data is dynamic, it can grow. The size, you know, could be out of control, right? Yeah, yeah. So if you allocate 1,000 bytes, yeah, sooner or later, it's not enough, right? Yeah. So then, 1 million bytes, yeah, yeah, probably after some time, yeah, not enough. Yeah. The question, how to make sure your storage space always sufficient to hold the dynamic data. Another technical problem you need to solve. Yeah. 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 How to control your array size such that you always have sufficient storage locations for your incoming data. Yeah, incoming data, you need to have some locations for the incoming data, right? Yeah. How do you do that technically? Yeah. So you need to do some special arrangement. Yeah. So here we talk about the idea. Okay? Yeah. All right. Yeah. Yeah. All right. Certain relation of one. So that's a question. That's a big question we need to answer. Okay? Yeah. So here, yeah, let me, you know, skip it temporarily. Yeah. Later, we will come back to this question. All right. Now let's look at how much space is sufficient. How to tell, right? How to tell? Okay. You cannot say, you know, 1 megabyte or 1 gigabyte sufficient. Yeah. Because at the beginning, when you do not have a lot of data, if you allocate 1 gigabyte, you waste a lot of space, right? Yeah. Because if you allocate 1 gigabytes to your array, most of the time, the space wasted. The space wasted, okay? Yeah. Because that amount of space, if you do not use that amount of space, you can use for other software, right? Yeah, you can use for, other software. Yeah, yeah. But if you allocate to the current array, then you cannot touch it, okay? Other software, you cannot use this space already occupied. This space already reserved. You don't want to, at the beginning, you reserve 1 gigabytes, right? Yeah. When your data amount relatively small, why you reserve 1 gigabyte? Okay? Yeah, wasted. So at the beginning, you should use relatively small storage space for it. Yeah. When it grows, then you increase the amount of storage space. Yeah. On the fly. So you increase the storage space on the fly. How about that idea? The question is, how do you control? How do you make it work? You maintain your storage space on the fly. How do you do that? That's the question. Okay. Now, we want to solve that technical problem. Yeah. All right? Yeah. Yeah. All right. Here, I use a simple diagram to describe the idea. So how do we manage our memory space efficiently, on the fly? Yeah. All right. Make array space sufficient for dynamic data. Yeah. All right. It is unknown about amount of incoming data. Yeah. So at the beginning, we use a relatively small array size at the beginning. Yeah. But the array, we know, the array property, the size is fixed, right? Yeah. Because after you declare array with certain size, you cannot change the size. That's the array property. Must be fixed. Okay? Because when you declare array, you ask the operating system to allocate certain amount of space to this array. After that, you cannot change it. You cannot change it. Okay? Unless you destroy the array. If you change, you destroy the array. Yeah. That's okay. You throw away this array, then you create a new array. Then you can change. Your new array has larger size. But the old array, you replace the old smaller array with a new larger array. That's the way you change the size. But the old array, you have to, release the memory. Yeah. Replace it by a new array, the old release the memory. You don't want to occupy the space of the old array. Yeah. Yeah. All right. Idea. Yeah. Assign certain amount of space to an array initially. Yeah. Yeah. All right. Yeah. Not too much. Okay. Certain amount of space. Yeah. Keep adding data and monitoring the size closely. Yeah. Yeah. All right. So here, you need to, when you declare array, you need to specify certain size of the array. Okay? Certain size. So this array can store this many data items. Yeah. 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 All right. Certain number of data item. So that number we call capacity. Okay? But capacity, you use the number of storage locations gradually, right? Yeah. So, yeah. The part that is used, okay? Yeah. This part, yeah. And the unused part, okay? Yeah. You have some room, okay? Within the capacity, yeah. So you grow the storage size. So there is a real size number, right? There is a capacity number. Then the real data size, another number. Okay? Yeah. All right. So here. But when the size number approaches the capacity number, then you need to think about, at a certain point, you think about replace the old array by a new larger array, right? Yeah. That's the idea. Yeah. Replacing old array, yeah, because, you know, you will run out of space. You need to add more storage locations. Yeah. All right. So you need to monitor the, you know, remaining amount of space. Yeah. All right. When a threshold is reached, yeah, probably you want to, because when you do the monitoring, you need to set some threshold, right? Yeah. Set some threshold. Yeah. Before the threshold, yeah, you do not worry, okay? At the threshold, yeah, it's like a warning signal. Yeah. Let's say 90%. When you use up 90% of the space, only 10% of the space locations available, then you need to think about transition, right? Yeah. Yeah. Data transition to a different array. You need to start preparation. Yeah. Start some early preparation when you hit that threshold. Here, let's say 90% line. Okay? Yeah. Yeah. All right. Yeah. New array. Copy to new array. Yeah. All right. Copy data to new array. But we know data copy, if your array size is big, your data copy is pretty expensive. That means takes a lot of time. Data copy takes a lot of time. You need to think about that. Okay? Expensive to copy a large array. The time used, yeah, large. Here, when I say this expensive, that means use more time. Okay, yeah. We look at the data copy. It takes time. Okay, large array data copy. It takes time. Yeah. But when you spend your time on data copy, yeah, there, your program, it looks like your program freezes, right? Because your program, you need to spend the CPU time on data copy. There, the CPU time cannot be used doing the operations, right? Yeah. So then, you know, suddenly your program freezes, okay? For a few seconds. Think about that. So then your users, your customers do not like that, right? Suddenly it freezes. Let's say freezes for 3 seconds. It's not acceptable, right? Yeah, 3 seconds. It's a reasonable time to make a large data copy, right? 3 seconds, reasonable time. But for your customers, they cannot tolerate. Yeah. So when they work, suddenly it freezes for 3 seconds. Yeah. So they will be very mad, right? Even 3 seconds. After even 1 hour, 2 hours, then freezes 3 seconds. Yeah. So they feel very bad. Yeah. So we need to solve that problem. How do we copy the data gracefully without 3 seconds, you know, freezing time? That's another technical problem we need to solve. Yeah. Now we want to do some smart way to do the data copy. So copy the data gracefully without any delay. Yeah. So our customer, nobody will notice that delay. How about that? Is it possible? Yeah. We do the data copy, but nobody noticed that. Okay. Yeah. Is that possible? So, yes, we can do it. Here, I described the idea. Yeah. So, yeah. All right. So here, let me give you the idea. Yeah. All right. let's assume the data copy, this peak represent, yeah, because when you hit some point, suddenly you need to spend your CPU time on that data copy. So the CPU time that can be used for your current program reduced to minimum. Okay, suddenly reduced to minimum. Okay, yeah, because before your new array is available, you cannot touch the array. Yeah. If you touch array, which array do you use? If your old array, you will use up the space quickly, right? So you have to stop using the old array. Yeah. Then you do the data copy. Transition to the new array. Before you are ready, you cannot allow the user use the new array, right? Because you haven't completed the copy. You do not allow the user use the new array. So that period of time, your customers, they have to wait. They have to wait. Now we want to fix that problem. That waiting time problem. Yeah. Let me see if I have enough time to complete this story. Yeah. Only 5 minutes. Yeah. Let me try. Yeah. Probably it's enough. 5 minutes. Yeah. Now we do this way. Yeah. Remember, the expensive means the time used for data copy is high. Okay. The time used for data copy is this high. Okay. This high. Yeah. Here we can say, this height. You can imagine, this height is 3 seconds. Okay. Yeah. 3 seconds already. Quite a lot. Okay. So here, we want to reduce the 3 seconds to 3 milliseconds. How about that? If you make your customers waiting 3 milliseconds, it's not a big deal, right? 3 milliseconds. So nobody can notice that, right? So we want to reduce 3 seconds to 3 milliseconds. That's the goal. Yeah. How can that happen? Yeah. So we do this way. Yeah. So we do not allow this peak. Okay. This high peak. Yeah. We do not allow that. The question: can we spread this heap? We can spread it out. We do copy. We spread our copy in a longer period. Here, your copy occurs in this shorter period, right? We can spread the base of the heap longer, stretch, but the height, we compress the height much lower. Can we do that kind of thing? Yeah. So the idea is we try to spread out that data copy period, because now we will use a much longer data copy period. Longer period to do the data copy. Okay? Yeah. Then when we do the copy, because we only need each time when we do the copy, we only need to use 3 milliseconds. Then we do some work. Then next time we do another 3 minute copy. Then do some normal work and so on. Yeah. So here. Yeah. Let me use the last 2 or 3 minutes to, complete the final part of the story. Yeah. So we do this way. The threshold, as soon as the line hit, the data, new data hits that 90% line, then we create a new array. The new array double the size of the old array. How about that? Double the size. All right. Yeah. After that, then we copy the data, but we do not copy all the data. Okay. Yeah. If we copy too long, okay. Can we just copy when one data piece comes in? Can we copy 10 pieces of data? 1 to 10 ratio. How about that? 1 to 10 ratio. One data item comes in, we copy 10 older data items to the new array. How about that? After 10 items copied, then we stop. We stop copying. Okay? We do the normal work. Yeah. But when we copy 10 data items, we only need 3 milliseconds. Okay? Then we do the normal work. Then another data comes in, then we copy 10 more. Okay? When new data comes in, we copy 10 more. Every time 1 to 10 ratio. After you copy, after you get the 10%, because when the remaining 10% data come in, you copy 100%, right? Almost, because 1 to 10 ratio, your copy part is 10 times of that, close to 100%, right? That's the, copy all the data gracefully to the new array without long delay. With, 3 milliseconds, that, tolerable, yeah? So nobody noticed that. Yeah. That idea, think about. If we do that way, so here you can see, in the real world situations, you need to solve technical problem like this all the time. Yeah. All those, little things, you need to find solutions. Yeah. All right, yeah, so let you go. Yeah. Next time, let's continue. Yeah.